The final topic we need to discuss is polar coordinates. And if you've seen polar coordinates before, you'll remember that it's a way of rewriting the XY plane in terms of two other variables. So the first one is the distance from the origin, right? So I'll go ahead and color in the origin in purple, and I'll pick some point in the XY plane. Right, so let's call this point P. And P has some coordinates, X and Y. It looks like, let's see, about 3.5, 3.5. It's probably about the XY coordinates that I have for this point. Now I can also express P in terms of alternate coordinates. Right, so I can express the point P in terms of the distance between the point and the origin. Okay, so I can also define what I call a radius, and that is the distance between the point P, so the coordinates given by X and Y, and the origin. So the formula, and we usually call this R for radius, right? It's because it gives the radius of the circle that P lies on. And so we define R, which is a function of X and Y, and the formula for that is the square root of X squared plus Y squared. So just the distance to the origin, okay? And then in addition, right, in addition to having a radius, notice that, right, so notice that the entire circle that P lies on has the same R value as P, right? And so we want to distinguish a particular value for P. So we want to know what is the angle, right? What is this angle in the plane? So we usually call this theta. Okay, so then we also have a value theta, and we can define theta as the inverse tangent of y divided by x. And so the advantage of doing this is it allows us to describe certain functions that would be very complicated in x and y using simpler parameters. Okay, and so just to give you some examples, if I had something, let's pull up a new page here. So let's suppose that I had a function. Let me go back to black ink. Let's suppose that I had a function something like 1 over the square root of x squared plus y squared. Right? When written in x and y, it doesn't have a very nice formula. But let's go ahead and instead let's write a function. We'll just call it g just to distinguish it. And we'll write it in terms of r and theta. And you notice that in r and theta space, this function has a very nice formula. So g has the nice formula of 1 over r. Okay? And so there are other functions that we might want to define, right? So maybe we have a function h of r and theta, and so, maybe that's r times theta. If we were to write this out in terms of x and y, the formula is not so beautiful, right? Because the formula there would be the inverse tangent of y over x over the square root of x squared plus y squared, right? So that formula looks horrible, but it looks really pretty when we just express it in terms of r and theta. Okay, so let's go ahead and look at some examples, right? So, right, we can look at some specific examples, and I'll pull up this graphing software in a moment. So some specific types of examples might be, right, where you depends only on r. Right, so an example there might be, a f of r theta is equal to r. And you might have something that depends only on theta. So we could try writing f of r theta is equal to theta. Now there's a little bit of a problem. There's a little bit of a problem with this one. Also with our r times theta, and we'll see what that is when we graph it. It's still a function, but it's not what we would call a continuous function, and you'll see why momentarily. Okay, so let's go ahead and pull up our quick graph here. And let's start with the function z is equal to r, right? And that function, you can see, it's sort of the equivalent in three-dimensional space of the function f of x equals the absolute value of x, right? So in single variable calculus, that gave us a function that was essentially the distance to the origin. And so the two-dimensional surface that's the equivalent of that graph is actually a cone, right? And so you can see that it comes to a sharp point at the bottom. We'll learn about derivatives very soon, and in the same way that the function absolute value of x was not differentiable, we're going to have a problem with this function at the origin. But it still is it's a well-defined function in polar coordinates, and this particular one is continuous. Now let's pull up the function z is equal to theta. Let's zoom out a little bit, right? And so here you can see that, I go from theta, and we'll use mainly radial coordinates, so a radial representation of angles in this class. So I start out with an angle theta equals 0, right? And that's right along the x-axis. So we're looking now at theta equals 0. And as I curl around, right, the axis and increase the value of theta, it'll go all the way up to 2 pi. Now the problem is you can see that this function isn't continuous because once it makes a cycle around, the z value is at 2 pi when I come back around to the x-axis, right? So this particular function is not continuous. Now an example of a function that is purely dependent on theta but is also continuous is the function z is equal to sine of theta, right? And so here you can see it has some, you can see that it has some corners or weird cusps in it, but it is a continuous function, right? And also when you're working with this graphic calculator, notice that if you tap twice on the screen, the surface will become just a spray of dots. And if you tap again, you can get a mesh. And sometimes when you're looking at a function that's a little bit weird, it helps to make a mesh out of it so you can really kind of see what's going on a little bit better, right? And then if you go ahead and tap twice again, you'll get a nice surface back. All right, so I think that's pretty much what I would like you to know for now about polar coordinates. We're going to go ahead and revisit them later in the semester when we talk about changes of coordinates for integrals, and you'll see that integrating certain functions with respect to polar coordinates can be easier in some cases than if you try to do it in XY coordinates. But for the moment, just understand how to graph functions in polar coordinates, and also understand the difference between a continuous function and a discontinuous function. And really the variable theta is most likely to cause you problems in this respect, right? Because theta itself is not a continuous variable, which we saw when we had this graph here, right? So theta is not a continuous parameter, and there are certain places where we have to take a little bit of care with respect to theta when we work with polar coordinates. But more on that later. For the moment, you know what you need to know.